it's impossible to get a good understanding of forces without talking about the contributions of Isaac Newton. In the late 1600s and early 1700s, the things that Newton was able to discover and give meaning to helped set the course for physics for the next 150 years and beyond. And in fact, in many engineering and modern applications, we still use Newton's models, even though since then we've come up with slightly more accurate models in special situations. But he gave us models about gravity and motion, even did some stuff related to the nature of light, and in his spare time happened to invent something called calculus, which is one of the most essential mathematics forms used in science. But he also spent a great deal of time studying inertia. Building on the experiments of Galileo, he and other scientists had noticed and tried to study this concept of inertia. And inertia is the name for an object's unwillingness to change from its present state. And it was observed that all objects seem to have this property. So if an object is at rest, it wants to stay at rest. But they also observed that if it was moving at a constant velocity, it would want to stay moving at that constant velocity. For example, if we could throw a rock in deep space and there's nothing around to stop it, it would just keep doing what it's doing. A good way to think of inertia is to imagine picking up a heavy rock in one hand and a marble in the other, and then moving both hands really quickly side to side. And you can even try this at home if you have something heavy like a rock and something small and light like a marble. Move them both side to side in your hands. And you'll notice that the rock feels heavier compared to the marble, not just in your hand, but it also feels harder to move back and forth. It won't move as quickly back and forth in your hand as the pebble will. It won't move as easily. That's because the rock has a greater inertia, a greater resistance to its changing state. So heavier objects in general have larger amounts of inertia than smaller ones. And that's why the rock is harder to move than the marble. But Newton didn't want to just to state the law of inertia. He wanted to come up with a full law that explained why, in some cases, an object breaks from its inertia. Because we know that objects don't always stay in constant velocity. They also don't always stay at rest. There are cases when they accelerate. And so Newton did his best to explain that in what became his first and one of the most foundational laws. He said that objects at rest want to stay at rest, and objects in motion want to stay in constant motion. That first piece is really just stating what inertia is. It's the second piece that's just as essential to the definition, though. This is Newton's critical additional step. He said they'll remain at rest or in constant motion unless acted upon by an unbalanced external net force. Meaning, the unbalanced part means that you're dealing with forces that aren't all completely canceling out. The external part means that it's coming from some outside source. So not forces within the object, but some other objects around it applying some external force to it. And we know what net force means. So the only time objects will break from their inertia is when they are acted upon by an unbalanced external net force. So while Newton's second law obviously has a lot to do with inertia, it's not just a law of inertia, it's a law that explains the only conditions under which inertia can be broken. We can also then use this concept of inertia, I just erase my lines here, we can use this concept of inertia to explain some other situations. So here we've got a tablecloth being pulled out from under dishes. Now, if you were just to do this at home, you'd probably notice that the dishes smash all over the place. In this case, though, I'm using the common magician's trick that you might have seen done in stage performances before. It's the trick where a tablecloth can be pulled out from underneath some dishes while keeping all of the dishes in their place. And we want to try and think of, how is this possible? How is it that a magician could pull a tablecloth out from under some dishes while keeping all of the dishes in place? Well, let's think about this. There is some friction between the bottom of each dish and the tablecloth. So what a clever magician might do is try and reduce the friction in between. So let's begin by writing that down, and then we'll consider what would happen in that case. So, if there is zero friction friction, or really I'm going to say 0 or almost 0, because the effect works well even though there still would be a tiny bit of friction involved. So 0 or almost 0 friction. Between the dishes and the table, or the dishes and the cloth, I should say. Well, what would that affect? Well, remember, it's that frictional force that the dishes are feeling connecting them to the cloth that would cause them to be pulled out when you pull on the cloth. Because we have to keep remembering that we're not actually touching the dishes, we're only applying a force to the cloth. So if there is friction between the dishes and the cloth, that frictional force will pull on the dishes when you pull the cloth. But a clever magician can reduce the friction by either greasing the bottom of the dishes or reducing normal force by doing a quick flick and making the dishes rise up from the table slightly. That can all help to reduce the friction associated with the dishes and the tablecloth. So if they can reduce it to 0 or almost to 0, then suddenly there's no frictional force acting on the dishes. If there's no frictional force acting on the dishes, that means there are no forces acting on the dishes whatsoever. So that's what we can jot down now. So if this is true, then there is no force acting on the dishes. Only the cloth. And so if there's no overall force acting on the dishes, then that means the dishes do not accelerate. The dishes must remain at rest. So again, the idea is that the reason why normally when we pull the tablecloth out, the dishes would go with it, is because there's some frictional force between the bottom of the dishes and the tablecloth. But if we can reduce that frictional force to completely 0 or almost to 0, then it'll feel such a small amount of force that it can't possibly accelerate and it'll simply remain at rest. This can also be a really helpful law to help us imagine what could be going on in deep space. Because in deep space, there are no particles or atmosphere, and there's no gravitational force from Earth, and so there are very few forces around at all to act on an object. And we're allowed to see Newton's laws of inertia in effect more specifically. So let's take a look at a rocket that was gliding sideways through space. And so at position A, we see it has no rocket thrusters out the back. So it's just gliding through space towards position B. But then when it gets to position B, it does turn on its rocket boosters. And so what happens from there? Why did we draw position C where we did? Well, once it turns on its rocket boosters, two things are going to happen. First of all, the thing we can't forget, based on what we know about Newton's first law, is that it will still continue to travel in that direction. The only thing that's changing is that it will also now travel downwards as well. The rocket thrusters are going to help give it some new acceleration in the downwards direction, but it's still going to continue to move towards the right while it does it. So that combination of continuing to move to the right while also moving down is what's going to cause it to move along that shape of a pattern. And that's what will take it to point C. But then if we want to think about what's happening after point C, well, let's imagine then that they turn their rocket thrusters off after that. We can think, where would it go from there? Well, it was gliding sideways originally, and then its rocket thrusters helped it to glide along this pattern, as we said. It will then just continue to glide along that pattern after that as well. And so that is where the rocket would end up at a later time. It would continue to travel not straight to the right, not straight down, but continue along the same path that it was before, even when its rocket boosters are turned off. And now with an understanding of inertia and when inertia can possibly be broken, it allows us to get an understanding of our next concept, which is inertial frames of reference. Now this would be a little bit easier for me to explain in class, so you can leave this part of the note for now. We're going to discuss it in class, and then I'll give you guys a little bit of time to try and answer the questions that you see below, trying to look at the situations that are given and determine if they're in what we would call an inertial reference frame or if they're in what we'd call a non-inertial reference frame. And you can do your best to read the definition yourself if you want and try and understand it, but again, we're going to go through some specific examples in class and try and make sense of what those two reference frames are, and also talk about something at the bottom that you see there called the fuzzy dice test, which is something we can use to help determine what kind of reference frame we are in. But again, all of those things are things we're going to save for class time. So as long as you've gotten everything up until this point, you can save it until you come into class.